Hey, what's up, guys? Yeah, so today I want to talk about discrete Fourier transform and fast Fourier transform. So to be honest, that before I come to America, that I didn't know, I didn't know this kind of things. And I think the DFT, the discrete Fourier transform, is not difficult, but the fast Fourier transform is a really amazing idea. Okay, so since I'm from math and physics background, so the first time when I did fast Fourier transform, so great. Okay, I cannot come up with things. I cannot come up with these things. So this is my video that I try to interpret, describe the quick and the DFT and the FFT idea, more theoretical way. I hope you guys subscribe to my channel. Okay, so before we do this, so this is discrete Fourier transform and the fast Fourier transform. So before we do this, let's quickly remind the complex roots of unity. Okay, so omega, let's define omega equals n is 1. So usually omega is exponential 2 pi I divided by n. Okay, so some notation will use omega n. Okay, so I will do this. And this obviously that this omega n is a complex number. So if you take the omega n generated, then it will be a cyclic group, if you know the group theory. Okay, which is abelian. Okay, so yeah, that's it. Okay, so the roots of this, let's say this x, the roots of xn equals to 1 is the omega n0, omega n1, omega n2. So n2 means that omega n squared up to omega n minus 1. Okay, so these are all the roots of xn equals to 1. And by the theorem of fundamental theorem of algebra, this equation has n roots. Right? So we find n roots. Okay, so that's it. Okay, so the quick lemma, which is almost trivial, is that if you do omega n to the, if you let's say you do dn and dk for this one, so this means that this is exponential 2 pi I divided by nd times dk will become exponential 2 pi I k divided by n. So this is omega kn. Okay, so this is just a trivial lemma. Okay, so this is a trivial result that we will use. Actually, the idea is very trivial. Okay. Okay, and another very simple example is that if you consider n is even, let's say n is even, then you take omega n to n divided by 2, that you get exponential 2 pi I divided by n divided by 2, you get exponential pi I, which is minus 1. Okay. Okay, lemma. So this lemma is called a halving lemma. Now this halving lemma say what? Say that if n is greater than 0 and is even, and okay, then the square. Let me just write down. This is not difficult. The square of n roots of unity, the square of n roots of unity is, I should say r n divided by 2 roots of unity. Okay, so what hell is going on? So this means that you take n roots of unity, let's say exponential 2 pi I divided by n, right? And then k, and then let's say n is even. Okay, and if you do a square, if you do square it, right, you square, you get exponential 2 pi I 2k divided by n, which n is even, so you can write 2 pi I divided by k and divided by 2. Okay, so which you prove the results, right? Very stupid. The square of n root unity are n divided by 2 roots of unity. Okay, so perfect trivial. Actually, the first Fourier transform idea comes from this very simple observation. Okay, and I mean, you can easily check that if you square, if you compute this n 2k n divided by 2, which is easy to prove that is n and k, which is just 1. Okay. Okay, another lemma, which is also used in a quantum computation, called the summation lemma. Okay, so this lemma is that let's say you choose n greater or equal to 1, and then you take another integer, let's call it k, and then you compute the greatest common divisor is 1. That means that k and n are co-prime to each other. Then okay, no, I think we don't need this. Okay, the only thing we need to use is that the k is not divisible by n. Then if you sum over omega n k up to j, where j from 0 to n minus 1, this will give you 0. Okay, so what this means? Let me just do some example. Let's say do the first stupid case. Let's say n equal to 3, and then j choose to be 1. Okay, sorry, k choose to be 1. Okay, then you can see that this will become the 1 plus omega 3 plus omega 3 squared 0. This is obvious. If you plot in the two-dimensional, right, you get a three-dimensional vector. You get 3 vectors, which is sum is 0. Okay, so this is basically some symmetric property that you can imagine that if you choose n to be some large, right? Let's say n equals to 8, then you separate into the a vectors. Okay, so quickly go to the proof. Omega n k to the power j from 1 at 0 and minus 1. So this is what? This is the geometric series, right? So we just use the geometric series summation. So we get omega n k minus 1, omega n k n minus 1. Okay, so notice that this is true because k is not divisible by n. So this means that omega n k is not 1. Okay, so that means I can use this formula. Okay, and simply compute, right? You n k n minus 1, omega n k minus 1. So this is 1 minus 1, omega n k minus 1, and this is non-zero, so this is 0. Okay. You can see this type of proof is very trivial, right? Compared to like we do analysis, we do design number theory, which is very difficult. But for this type of computer science proof, this one at least simple. Okay, so let me just define the DFT. Okay, so what is the DFT? Okay, so let's consider a polynomial at f x, then go to aj xj minus 1, and sorry, j from 0 to n minus 1. This is j. Okay, so this is like the degree j polynomial, and the Fourier transform defined to be the following. It's like okay. So let's take the coefficient, right? You can make a coefficient x a vector, so you get a0, a1, up to a minus 1. So this is a vector, right, in the n dimension. And I define the Fourier transform to be the following. I define yk defined to be a omega nk. Okay, it means that the summation aj omega nkj, j from 0 to n minus 1. And so we got k equals to 0, 1, 2 up to n minus 1. Okay, so you start from this a0, a1 up to an minus 1, and then you can collect y0, y1 up to yn minus 1. And then all these y vectors are called the discrete Fourier transform. From a0, a1, an minus 1. Okay, so mathematically, it's just simple by definition that yk is just this. Now, simply speaking, that you just write down matrices which is composed with this omega, and just a linear transformation. Okay, so this is just a linear transformation. Okay, so one can write y equals to DFT n a. Okay, so now you should view a as a vector. Okay, so who cares, right? So okay, the key point is that if you use this formula that suppose you get n vectors, And the number of steps that you need to compute a discrete Fourier transform is you do the matrix multiplication, right? So let's say you get this n by matrices, and you get something. So times these, times these, times these, times these. So you can see the total takes O(n) squared time. Okay, so the fact that if you use the so-called fast Fourier transform, only takes n log n time. Okay, so this is like a main improvement compared to the previous one, right? So this is why I need to film this. I think this is interesting. So this is why I film this video, right? Otherwise, that discrete Fourier transform, just some simple definition. Okay, so idea. So the idea is the following. Okay, so idea is that in order to prove this, let me just do some simple assumption. Let's assume that n is a power of 2. Okay, so that means let's say original a of x looks like this. So we need to use some polynomial to help us to get something interesting. So let me just write as I can write as, let's say, I can take out the even part and odd part. So let me just write a0x. Okay, so an a1x. Okay, so what is a0x means? Don't worry. So let me just write down. So a0x is the even part, right? So a0, a2x, a4x squared. Don't worry. What I write is true. Okay, so I separated, but I downgrade the polynomial. So I view a0, a2, a4 up to a minus 1 as a new coefficient. And the a of 1 I define to be r of 1. So I get a1, a3x, a5x squared up to a minus 1 xn divided by 2 minus 1. Okay, so which tell me that if I want to reconstruct this polynomial, that the first one I need to take what? I can take x squared, right? I can take x squared here. And I can also take x squared here, but I take x squared here, that becomes x squared, right? But this is a3, so it should be x cubed. So I should take x. Okay, so this is the recursion relation. Okay. Okay, but obviously that you see something interesting, right? Because this is x squared. Okay, so as a proof that our simple lemma that is here having lemma, if n is even, then the n roots of unity are n divided by square of its n divided by roots of unity. Okay, so which means that if you see this formula, right? This formula tell you that this guy is actually the Fourier transformation of, the Fourier discrete Fourier transform of this a0, a2 of the n divided by 2, and this is a discrete Fourier transform of a1, a3, a5 up to an minus 1. Okay, and so which tell you that if you denote t of n to be the number of steps, multiplication steps that you need to do the DFT, and then this tell you that t of n is 2t n divided by 2 by the having lemma. And the plus the steps, right? So you just add them just very simple, right? Because polynomial at most n degree, so it takes at most n steps. And then you can use the master's theorem, or you can see that this equation is exactly the same as the merge sort. So maybe you heard about merge sort. Then you can prove that t of n is n log n. Okay, so this is a highly abstract idea that you can do this. So idea is that you break the n, you break into 3, and you separate it 2, and then you just keep recursive call, then you can get this one. Okay. So I don't want to talk about detail. Okay, but you can go to online and find detail. But this is just a quick observation that why you can do this faster Fourier transform in n log n time. And the detail you can just go online, right? But I need to I like to do the abstract way. Okay, see you guys next videos. Hope you guys subscribe to my channel.